Hello viewers, I'm Kausalya. Today we are going to solve problems related with Norton's theorem. The problem is obtain the Norton's equivalent across terminals A and B for the network shown below. So here this is the given circuit diagram. Here and A and B are the terminals here. So we have to draw the equivalent circuit. So as we all know, a Norton's equivalent circuit will consist of a short circuit current and a resistance or impedance connected parallel to it. Right. So here the first step is calculating the short circuit current. So to calculate the short circuit current, the first thing is we have to short circuit the terminal. Right. Here A and B are the terminals. So here these terminals are short circuited by a conductor. Right. Now we need to calculate the current that flows through this path, that is known as ISC. So here you see the current, right? It flows like this, and once it reaches this junction, what happens? The current gets divided into two, right? Then the current which flows through this path, it flows through this 2 ohms like this, and again through this AB terminal, right? It comes back and again flows through this 3 ohm, and the circuit gets closed like this, right? So here it is clear, right? You see this 2 ohm and this 3 ohm are in series, right? Since here we are having a short circuit, that is we have short circuited this terminal, no current will flow through this capacitor, right? So because the current will always select the least resistance path. Now the value of short circuit current is calculated as, right, here by using current division rule. So this is your total current. This is in polar form. Here I have represented in rectangular form, right? Total current into opposite resistance. So we need to calculate the current that flows through this path, right? That is this current we need to calculate. So the resistance which is opposite to this path is J15 ohms, right? Therefore J15 divided by the total resistance. So here the total resistance is J15 plus 2 plus 3, right? So finally this is our expression. So when you solve this, we are finally ending up with the answer as 9 plus 3J amps, right? So this is the value of short circuit current. The next thing is to find the Z Thevenin. So to find the Z Thevenin, what we have to do? We have to remove the voltage or current sources, right? So when you remove voltage or current sources from the given circuit diagram, our circuit will look like this, right? So here in this case, again Z Thevenin we have to proceed from backwards. So you see, assume a current which flows like this. So when it reaches this junction, what happens here? The thing is the current gets divided, right? So here this current will flow like this, and again when it reaches this path, here it is an open circuit, so no current will flow. So therefore the current flowing through this 2 ohm will flow through this J15 as well as through this 3 ohm, right? Can you understand? Yes. Now what happens? Since the current gets divided between these two, they are said to be parallelly connected. And the next thing is, since the current flowing through all these three elements remain the same, these three elements are said to be in series, right? And that combination comes in parallel with this J5, right? Sorry, here it's minus J5. And now the formula is Z1 into Z2 divided by Z1 plus Z2. Right. So Z1 is minus J5 and Z2 is J15 plus 5. Right. Divided by total resistance is minus J5 plus 5 plus J15. Right. So once you solve this, finally we are ending up with 1 minus J7 amps or 7.071 with an angle of minus 81.86. Sorry, this is not amps, this is ohms. Right. So we have calculated the short circuit current and we have calculated the Z Thevenin. Now finally we have to draw the Norton's equivalent circuit. So finally this is our Norton's equivalent circuit for the given diagram. Right, we are having a short circuit current and we are having an impedance which is connected parallel to this, right? this problem gets over here. We will proceed with the next one. So our next problem is, in the circuit shown below, compute the current through the zero resistance ammeter. Use Norton's theorem. So we need to calculate the current that flows through this path, right? So this is your given circuit diagram, and here this circuit has 3 loops. So here we are having 3 loop currents, right? I1, I2 and I3. Here you see in loop 1 and loop 2 there are no current sources, so we can assume direction either in clockwise or in anti-clockwise. It's up to you, right? And here, since we are having a voltage source, we are always assuming the current flows from minus to plus, so the direction is like this. Then the next thing is to find the short circuit current. What is the thing we have to do? So regarding a bridge circuit here, you see the terminal is AB, right? And there is no resistance value here. Simply there is an ammeter, and that too you see they are clearly mentioning it as zero resistance ammeter. There is no resistance in the path, right? So the first thing is we have to frame the matrix. So when you frame the matrix, the same thing, V is equal to IR, right? So I believe you people know how to write this matrix. So here in this case, there is no voltage source in first loop, no in second loop, and there is a voltage source in third loop. So here you have to write it as 0, 0, and since the current flows from minus to plus, it is plus 20, right? So 0, 0, 20 here. And the respective currents are I1, I2 and I3, right? Then the next thing is we have to write the values of resistors here. This is a resistance matrix. Since we are having 3 loops, write it as 1, 2, 3, and here also 1, 2 and 3. Right. So again, this diagonal elements are nothing but the total value of resistance present in that loop. Here, this is the summation of resistors in first loop. This is the summation of resistors in second loop, and this is the summation of resistors in third loop. So just when you look at this loop, you see the sum of resistors are 8 plus 5, that is 13. Right? The next one is 5 plus 2, that is 7. And here 8 plus 2, finally it is 10. And depending upon the direction of current, we will assume plus or minus for the remaining elements. So the next element is the element which is common between your loop 1 and loop 2. So when you look at loop 1 and loop 2, there is no common resistor. So simply write it as 0. Right? And the next thing is between loop 1 and loop 3. So this is your loop 1 and this is your loop 3. So here see, for loop 1 the current flowing, that is the common resistor, is 8 ohm. So loop 1 current flows in this way. And in loop 3 the current flows in opposite way. Right? Therefore here we have to write it as minus 8. And the next thing is the element which is common between loop 2 and loop 3. So when you look at this, this is loop 2, this is loop 3. What is the element that is common? 2 ohm is common. Again, now look at the current direction. So here the current flows like this, and again here the current flows in the opposite way. Therefore here you have to write it as minus 2. Right. So this is our matrix. Then we have to proceed with the value calculation of del, right? And del 1, del 2, depending upon the things what we need. So here the first thing is we need to calculate the del. So when you calculate del, you see, solving a normal matrix, taking determinant. So here the answer ends up with 410. The next one is, here you see, we need to calculate the current that flows through this ammeter, right? So when you look at I1, it flows like this, and when you look at I2, it flows in opposite way. So you need the values of I1 and I2, and once you subtract I1 and I2, then we will get the current that flows through this ammeter, right? So for that we need I1. So to calculate I1, what is the formula? It is del 1 by del. So we need to calculate del 1. So how to calculate del 1? From this resistance matrix, you have to replace this first column with this element, right? So here once you rewrite, it is, this is your del, right? Again calculate the value of, this is your del 1. Now calculate its value, it is 1120. Again for del 2, you have to replace this column with this value. So when you write, finally the value of del 2 is, it is 520 here, right? Now I1 is del 1 by del, just substitute the values, and I2 del 2 by del. Now the current through this ammeter is these two currents are opposite to each other. Therefore you have to subtract. So just subtract, here the value is 1.462 amps, right? The next thing is to find the RThevenin. So what is the thing we have to do? To find the RThevenin, we have to remove the voltage source there. So just our circuit gets modified like this, right? So that is between these two terminals we will be having a voltage source. Once you remove the voltage source, you see here these two ends are connected by a wire. That's it, right? So this is your RThevenin, and A and B are our terminals, right? So here when you look at this terminal, what happens at this terminal? The current gets divided. Similarly, in this terminal, the current gets divided. Therefore, these two resistors are parallelly connected. Similarly, these two resistors are also parallelly connected, right? So how to calculate the RThevenin? Here the formula is again 5 into 5 by 5 plus 5, right? And for this 8 into 2 by 8 plus 2, and these two combinations are in series, right? So once you solve here, the final answer is 4.1 ohms. Now we have to draw the Norton's equivalent circuit, right? So here the Norton's equivalent circuit is, we are having a short circuit current, we are having an RThevenin, and this is the terminal across which we need to calculate the current here. So in this case, you see this current, the entire current will flow through this terminal, because the current will always select the least resistance path. Therefore, the current through this ammeter is nothing but 1.462 amps, right? Here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.